but it's the way the world works.
Now, that setup is how you test for the wave-light duality. It's the same experiment, it's just run a little bit different. And the wave-light duality is that if you put that beam through that space, it looks like dots. If you're looking for dots. If you put it through those spaces and you're looking for waves, light looks like a wave at the same time. And what Einstein discovered, again intuitively, because there's no lasers at this point, you can't really run the experiment yet this way. What Einstein intuited was something that we'd asked about for a long time, which is, what is basic matter? What is there? And we had waves, particles, but we also had this notion of maybe an ether, maybe it's passing, all this stuff's passing through an ether. Maybe there's this third other kind of substance that we're not really familiar with. But things are either particles or waves. You run this experiment in a little different way, and what you find out is that light, the quanta, the smallest little bits of light, are both particles and waves, depending on which you look at. And Heisenberg's uncertainty principle comes in that says it depends how you look. If you're looking for particles, you find that light's a particle. If you're looking for waves, you find out it's a wave. Well, you put that on top of measurement instability, on top of the space-time continuum, and at the beginning of the 20th century, physical science just has no idea what to do. It all goes because all of the none of the fundamentals are there. Okay?
An entanglement crushes our experience of space. Two objects, two electrons created together, are entangled. Send one to the other side of the universe. Now, do something to one, and the other responds instantly.
Without communication.
Instantly. So, either information is traveling infinitely fast, or, in reality, they are still connected. They are entangled. And since everything was entangled at the moment of the Big Bang, that means everything is still touching. Space is just the construct that gives the illusion that there are separate objects.
So maybe
down the rabbit hole yet?
Maybe entanglement helps explain the butterfly effect in chaos. And that's that something that doesn't seem to make any difference, that is a change in an initial condition, does make a difference somewhere along the way. When two electrons are created together, it doesn't matter how far away you move them. You can move them this far away, blocks away, miles away, across the planet, or across the solar system. And when you perturb one, the other is perturbed in exactly the same way, although there is no communication between them. It's called entanglement, and there really isn't any way to explain it. So the problem that we have is this. Whoops, I don't want him. I want him. The problem that we have is that, or it's not so much a problem, it's just, yeah, it's a problem. There isn't any hard line of demarcation between Newtonian physics and quantum physics. There's no hard line between the rules that affect big things, seem to work pretty well, and the rules that affect small things, subatomic particles, that seem to work pretty well, and we don't know where the line is between them. You'd think, right, that since everything's made up of little things, they're pretty important rules, because they underlie everything. On the other hand, sort of, you'd think, well, if it's a big thing and it works in a certain way, doesn't that make the little things inside work the same way too? We don't know where that line is. So, wave-particle duality, light's either both, either wave or particle or both. Quantum interference, an elementary particle can be in more than one place and can pass its trajectory, and that's another piece that comes out of that dual slit experiment with the laser. Superimposition, which is how we do quantum calculations, and that is those electrons and quarks, things smaller even than electrons, can be either on or off, or both. And that's where quantum physics gets a little weird. You know, we can go over there and flip that switch all day, and all you're going to get is on or off. There's just no, you know, you can make it seem like it's in the middle, but it's not. It's either on or off. And that's the way the physical big world is. But at the subatomic level, we can set those at on-off or on-off at the same time. And you get quantum mechanics at work then. But you'll also get all the uncertainties that go with it. Like Heisenberg's principle, which says you can't measure speed and location at the same time. Because you've got to stop something to make sure where it's located. You can't measure its velocity and its location at the same time. Heisenberg's uncertainty principle that says if you look at an experiment, essentially you change it. Now, we never thought that was the case. In fact, if you think about it for a minute, remember Descartes? I think, therefore I am. I reject it all unless you can show it to me in an experiment. Therefore I know that it is. He had no idea that looking at it changes it. But what Heisenberg in his era of quantum computing showed with these electrons and neutrons is that when you look, they change. You get a different outcome if you don't look than if you do look. If you look at them reflected, for example, you don't look at them directly, you get a different outcome than if you look at them directly. So looking makes a difference. Never imagine that. Entanglement, elementary particles separated can take on the same properties without communication between them. Uncertainty principle can accurately measure both motion and location, and interdeterminants in decoherence changing looking at the phenomenon tends to change it. And that's one of the primary physical problems with quantum computing. You got to get these electrons spinning. So you hit them with laser beams, and then you can get them spinning in both directions and both at the same time, and then you can do calculations from that. The problem is, if you try to pull out the calculation, if you look in there, the superimposition, them spinning plus minus and plus minus at the same time, disappears. So how do you calculate? If you go 1 plus 1 equals, when you hit the equal sign, it disappears. How the dickens can you make a calculator out of that? How can you make a computer? And the answer is you use mirrors. It's not smoke and mirrors, it's actually mirrors. If you look at a reflected, you collect a reflected image of those outcomes, you can calculate with that. You're not looking at it directly, and it doesn't make it break up, and it isn't a direct observation, so it doesn't change it. But it's very complicated. Because first you have a series of laser beams making a bunch of electrons go like this, and then you got to line them up in the right kind of superimpositions, and then you got to figure out what they're supposed to do. And the problem is, you throw all this in, and what you're not sure about is what's going to happen. I mean, we've turned a couple of these on, and they haven't put a big hole in the universe yet, right? But, you know, we worry about that a little bit. Why? Well, see, we're not actually sure at that level how these little buggers work. Part of what's interesting about quantum physics is we don't really understand it very well because you just don't know exactly how they work. Okay? So, little thought experiment here to illustrate, and also to illustrate the potential trouble. So, look through that space there, if you would please, or look toward that space. Okay? So, describe to me the phenomenon of doing that. What is it that happens? What are you seeing? What do you see and how do you see it? Yeah? Speak.
Reflected light.
Reflected light. Oh, you're seeing a reflection? Of what, roughly?
Wavelengths that we interpret as
Yeah, but I mean, what are you seeing reflections of, specifically, out there?
Plants and trees.
Okay, so there's objects out. What else do you see? Anybody see anything else besides what's out there?
The glass.
And what do you see in the glass, for example?
Nothing passive.
So, but you can see the glass, right? So you think about that for just a second. So you see through the glass, right? You get reflections back through, but you also see the glass, and you get some reflection from the glass, depending on the angle that you're sitting in and all that. Okay, so that's indeed electrons coming, sun bouncing off things, coming, hitting the photon, the photo things in your iris, and going to your brain, making you say, "Oh, green grass," right? Okay, all electrons. Okay, so I'm a little electron, short and stout. Okay, here's my handle, here's my spout. Okay, so I'm flowing in, right, in streams and hitting in here. Okay, so then how come you can see the glass? So some stop. Right? Don't come all the way through. In fact, when you see the glass, you also see reflection off the glass. So there's some that kind of stop there, in that sort of way. Okay? So let's say there's 10. 8 of them, I'll say 10. 7 of them come all the way through, you see grass. 2 of them, no, 1 of them stops, you see glass. 1 of them stops, you see a reflection. Here's the problem in the quantum world. How many did I add up altogether?
9.
That's the problem. There is in that phenomenon, in every phenomenon, using electrons, neutrons, and protons, every once in a while, an inexplicable loss of information. It disappears. It's like one of those photons hits the window, goes, "Oh, fuck it," and drops. Okay? And we don't know where it goes. Now, this isn't just a story your teacher's telling you. It's actually science. You can look it up. Okay. Now, anybody remember a big rule of science about things disappearing? What's that? Doesn't happen because of conservation of mass and energy. Right? Can't happen. Gone. Disappears. Doesn't exist. Where? So there are quantum theories that try to account for where it goes. Anybody heard about it? You know where does it go? What's that?
The multiverse theory.
Multi-universe theory. Into another universe. That every decision that electrons, protons, and even humans make is always a choice. I think I'll have a drink right now. Oh no, I don't think I will. And in one universe I had a drink, in the other universe I didn't, and in the third universe I did both. And if you multiply that out, it's pretty weird. If it happens every time that... Oh, but maybe it's not that. Maybe it's just one alternative universe, and all those electrons have dropped into that. But that still means that there's another dimension that we can't see, that we can't. But that the quantum world begins to sort of account for it. Now, what does that have to do with this class? We're making quantum computers. We're making quantum computers. And it wasn't interesting enough that we cloned Dolly the sheep, right? Without maybe everybody thinking about what all the... It wasn't enough that we start changing eye color, which we can do now. It wasn't enough that we start making predictions about... Now we're doing... Now I'm not saying we shouldn't, but the fact is we are, right? And we do not know the rules. Now, we didn't know the rules when we let the bomb off either, did we? Thought we knew what the rules were? You know, I've talked to a guy who worked on that project. I was at Oregon when the president there was from the Manhattan Project, and he spoke to us, and I spoke to him a number of times. those guys all, almost to a person, except for Fermi, who was kind of weird, headed for the ditch and said, "What the F did we do?" and spent the rest of their lives trying to undo it. To a man and a woman, except Fermi, who really liked it. You know, so we're doing quantum physics, and maybe creating computers that are really at a different level, such that pretty much all of the rules we talk about through a class like this, all the theories pretty much just kind of go away, because it's so exponential in terms of ability, computing ability. So I'll give you an example. We're working right now, I think the number's up to 18, I believe, entanglements. Superimpositions that are going on at the same time. They figure they get about 32, they might be able to actually have a working computer. Okay, so we're about halfway, a little bit over halfway, to what they think will be a working computer that will be kind of like computers that we have today. That computer will be able to solve a problem in 2 hours that we cannot solve ever. Now, period. And the math on that's a little too complicated, but it's with prime numbers, and I don't understand it either. But in 2 hours, that computer will compute that number and spit out an answer. And it's a computation that if we did it with real computers, the biggest supercomputer farm that we have available to us now, it would take infinity to figure it out. We don't know when it would figure it out for sure. We think someday it might. Couldn't figure it out, and that machine will do it in 2 hours, the new machine. But you got to get a whole bunch of electrons in superimposition and figure out a way to read the result. But it's an altogether different kind of phenomenon. New media will take on an altogether different kind of sense at that point, right? We might be talking about different dimensions, different ways of seeing things. The 3D of Avatar might very well might change